let's go ahead and get going today. We're going to go ahead and talk some more about the joys of the spine, and specifically the things of the spine that tend to bother everybody at some point in their life, which is unfortunately injuries. So like anything else, you can always have issues with different segments of the back. Typically, it tends to be the low back, and low back pain is a really fascinating thing because there's actually research studies that show there's a lot of people that if you actually were to MRI their low back, you would actually see they have disc herniations, but they don't actually complain of any pain. They don't have any issues with dysfunction. They're not really uncomfortable. Instead, just, they do have effectively a jacked up low back. Now, there's people that obviously do have disc herniations that have back pain, and that makes perfect sense. But then there's people that have no herniations, no easy to see imaging problems with their back, but they still complain of back pain. And what's even more fascinating is whenever you show the person that has the disc herniations, like, here's how your discs look, unfortunately, most of those people will then start presenting with back pain. So there's an interesting reality, which is if you don't know what's effectively jacked up or messed up in your low back, it won't bother you. But as soon as you know about it, then you start essentially having issues with it, because now it's something that you're aware of and tends to take away or concern you a little bit, shall we say. Now, there's obviously going to be soft tissue injuries that you're going to get from just the wonders of straining a spinal erector. Could be kind of, I'm sure everyone here has had spasms at some point in muscles, and obviously that can occur in your back. You can obviously have acute fractures, so that's literally from overloading from too much weight at once. It can happen with more of the facets, with hyperextension under very heavy loads, or just acutely heavily overloaded. We can have stress fractures, which is going to obviously occur from applying too much stress to those bones themselves, and again, tends to be issues with facets. Vertebral bodies can happen, but that's pretty rare. Disc herniations is obviously a thing. And then when the term whiplash comes up, what do you guys think of? What is whiplash? Yeah, typically car accidents. That's where, someone's gonna be driving along, they get hit, their head flexes forward extremely far and then goes backward at a very rapid speed, obviously faster than you can just try to headbang, so to speak. And that can overstretch not just the muscles, but the ligaments involved in your cervical spine, which is already relatively, honestly weak in nearly everyone you're going to meet. And then that can lead to a lot of other issues. And we've already established a little bit, we talk about it more in exercise phys, but it's an important thing here, which is a stronger neck actually is inversely related to concussion risk. So if you have a stronger neck, you're less likely to suffer a concussion, because you literally can use your neck as a shock absorber for any blow that your head takes. Whereas if you have a weaker neck, you don't have that same type of advantage. And so you're more likely to potentially have issues. So like anything else, things happen. Sometimes it's because of poor choices you made. Sometimes it's because of poor choices that other people made. And it's important to understand that, when this occurs, it's going to take a certain amount of time to resolve, because what's one of the major issues we have with our connective tissue and our bones whenever it comes to delivering nutrients to those tissues, guys? Bingo. They have to move to receive nutrients. Exactly, Luke. Because they don't have their own blood supply, capillaries going to them, the only way that you're going to get nutrient turnover is to move them. And that's really, really hard if you've got a disc herniation, if you've got these stress fractures, if you have whiplash, you don't want to move your neck. I mean, it takes time to resolve these issues. These tissues recover at their own rates, and you have to still move enough to help enhance that rate of recovery. Now, another thing to keep in mind, outside of the joys of everything we've covered, but what's really fascinating is disc herniations typically resolve themselves. So one of the craziest things that I've seen in the lit, which is if you have somebody has a true disc herniation, pain, issues with movement, blah, blah, blah. If you just start a clock, wait 6 months, they get better. Now, the crazy thing is that's why, people will be like, oh, surgery really helped. Chiropractic care really helped. Physical therapy really helped. Insert this other modality really helped. The reality is, sadly, most of the time, they heal on their own. Now, don't get me wrong, there are the points and the reasons for using each of those previous interventions. And I'm not saying that obviously all of those people are quacks and they don't do a good job. But what's really weird is the fact that disc herniations tend to resolve themselves. So your body does have the ability to heal itself. You can do things to help speed this up. And obviously, if we have issues with a disc being herniated, we don't want to have more compression through the spine. So what can we do to try to have less compression, or even putting some tension forces through the spine to help alleviate the pressure on those nerves?
Would I just be spending quite a bit of time laying down?
Yeah. Or you could do something where, have you guys ever seen an inversion table or inversion boots? So that's going to give you that same type of traction and allow you to invert yourself and have that type of extra recovery, so to speak, to those tissues. Yeah, I'll make sure I throw a video up on YouTube of me in inversion boots, and you can feel free to get a bit of a laugh. But it's still one of those situations where it takes a lot of time, and 6 months is a long time if you're in back pain. So now let's talk about happy little pictures of these things. So this is when we're talking about those stress fractures in those facets. Any of you guys have a friend or family member that got a stress fracture in their back from heavy lifting or otherwise? Or yourself? Okay. One of my friends actually got this from, of all things, doing really, really heavy cleans. And like anything else, it just took a while for it to recover, but it made it really difficult because anytime he put himself in a hyperextension, which is typically the position you really want to catch a heavier load. So he had to learn how to lift with more of a neutral spine, which takes time, especially when you're doing high speed, high power movements. Now, one thing that's an interesting thing to keep in mind is what's known as an osteoporotic vertebral compression or vertebral compression fracture, which is literally over a long enough period of times, you can compress the front side of your vertebral body down so that you've literally changed your posture forever. So how many of you folks have met an older person that like legitimately have that type of posture that it looks like they're sponsored by the letter, or by not necessarily the letter C, but by a question mark, because literally their tissues over a long enough period of time are going to compress, and they're going to literally be stuck in that hunched over position no matter what they do. Then also you have situations where the ligaments get lengthened, the muscles are obviously weakened, and so it's much harder for them to hold good posture. And that's why, you hear about conversations about, better posture, staying upright. And I kind of wonder how, obviously cell phone use is going to be affecting posture of this next generation of people coming up, since obviously we're spending more time than we would have otherwise in that hunched over position. Now, spondylolisthesis is going to be an issue where we literally have one bone slipping forward on another, and this is F-off painful, and nothing that I would ever want any of you guys to go ahead and go through, where literally you're going to see that one vertebral body is going to slide forward on the other. And obviously this is going to put a lot of torque, or not necessarily torque, this is going to put a lot of strain on the tissue, specifically the intervertebral disc. So you're much more likely to herniate it, and not to mention through that wonderful canal on the side, that's where your nerves go. So that's where you can talk about nerve compression. This is where when people have issues with back pain, they'll initially talk about how they've got a bunch of issues with their, they have like a burning sensation going down their hip or their leg. So it's going to be kind of like talk about things like, not necessarily sciatica, but major issues with obviously pain, discomfort, numbness, because literally those nerves are being impinged upon. And then spondylolysis, which is now looking at a fraction or fracture that we're going to get specifically due typically to more of a effectively a defect, which you're going to have between the vertebrae. And so over time, because of this little anatomical defect, it's not going to be able to deal with load like it should, which can then lead to stress fractures. And then this can eventually weaken things so much more that eventually they slip, and that's when you have the spondylolisthesis. And so, like anything else, there's a lot of things going on with the facet joints on the back of the vertebrae. And if we have enough issues and slight differences over what's optimal, if you're doing enough heavy loading, specifically you're not doing it properly, long enough period of time, you can obviously jack things up pretty bad if you're not careful. Yes, ow is definitely the operant term. So now when I say disc herniation, guys, this is what I'm talking about, where literally what you've effectively done is applied so much pressure that what's literally occurred is you've effectively shot the nucleus pulposa out of the damaged rings of our annulus fibrosus, so that collagen on the outside. And from here, this is going to be obviously a posterior herniation, where now it's compressing the spinal nerve. So everything that's involved in that nerve, which obviously can be not just innervating our muscles, but also with giving us the reception of information of, pain and otherwise, are going to be perhaps misfiring or firing too much. And obviously you are going to be very, very uncomfortable. And over a long enough period of time, like I said, typically most of the time it'll resolve itself, but obviously sometimes you need greater interventions to go ahead and resolve this. And it is incredibly painful. I've herniated a disc in my back before. I actually did that in college. Doing a garbage high box squat of like 365 or 385 and bouncing off of it, and I felt it go. Yeah, you can feel it just kind of like push out a little bit whenever it happened in my case. And then I got to really not lift anything heavier than a fork for about 6 months. So now, mind you, obviously since then I've lifted far heavier weights with better technique and through a larger range of motion than that. But at that point in time, if you're not absorbing, you're not controlling, you can have some major issues with that compression forces, because they're obviously not to be trifled with. Now, most of the time when this happens, it's usually going to be to the posterior, because our posterior ligament has a lot of different effectively gaps in it because of we're going through the spinal canal and otherwise. Whereas on the front side of our vertebrae, so the vertebral bodies, we have our anterior longitudinal ligament, which essentially wraps the entire thing. Still can happen that direction, but it's far less likely. That's why when you're lifting heavy, you should at least be in a neutral, so a neutral spine, or be in a hyperextended position, because you're less likely to herniate your discs, specifically when you're under heavy loads. Now, heavy loads doesn't necessarily mean that you're trying to squat or deadlift some massive amount of weight. Heavy loads also just involve just general impacts. Like you can herniate the discs of your cervical spine just like you can with your lumbar spine. So if you aggressively put yourself into a headstand, you're going to be putting a lot of force through those effectively very fragile tissues. And this is especially why for those of you guys that have had yoga with me before, when I'm teaching the headstand, I'm all about making sure, A, you're supporting yourself with at least your hands or your elbows, depending on your positioning. But second of all, you're always doing it with a good neutral, if not slightly extended spine position. Never doing it with a flexed or a rotated, because that's where we're talking about increasing that amount of shear and then the compression tension gradient you can have from one side of the vertebral body to the other. So it makes it, like I said, more likely that you're going to get hurt. And that's the last thing you're trying to do when you're doing something like yoga, which is usually about trying to make yourself feel better. So, yeah, and if this happens, it tends to hurt like an MFer, like real bad. Hard to take a deep breath, so on and so forth. Any questions about disc herniations while we're on it that you guys would like me to go ahead and talk about? All right, so congratulations, that's it. And then it's just basic zoom ins of the rectus abdominis, our internal and external obliques, so you can kind of see those angles of pronation. Then a little bit better imaging of it, along with some good old Erector Spinaes, and then looking at those semispinalis, capitis and cervicus, and thoracis. It's just obviously what it's going to be effectively origin or insertion into in those deep spinal muscles. Yay. So we are still cruising way ahead of schedule. What questions do you guys have for me as far as over any of the material we've covered so far, or we can go ahead and have you guys work on your projects some more today when you got, and have you guys do that in groups. Especially since I know we've got some obvious additions to these groups. So to review some math, we're working off Rollins first. If the effort arm is 20% closer than the point of insertion, which is 0.12 meters from the axis, and the resistance is 10 kilograms with a resistance arm of 0.45, how much force needs to be produced? Okay, when in doubt, draw it out. So first thing we're going to go and have is we've got our fulcrum, okay? We're going to then have our force pulling us down, and that's going to be that 10 kgs, and this is currently at 0.45 meters. Now, we're going to be lifting at 0.12 meters. Yes. Oh, wow. Now you guys are giving me more questions. I'm going to scroll back up. We had a little fun this morning. Okay. But it says it's 20% closer. So it's actually going to be here because it's going to be 20%. So we're going to multiply that by 0.8. So if we set this one up, we're going to have 10 times 9.81, because remember, right now we've got this in kgs and we need to multiply it by the acceleration of gravity so we can convert this into newtons, multiplied by 0.45 equals the effort, which is what we don't know, times the effort arm, which is 0.12, and that's going to be multiplied by 0.8. Because it's just 80%, 20% closer of that 0.12. So then we would go ahead and divide both sides by that sum here of 0.12 times 0.8, and then we would have our answer. Make sense, guys? Go and give me a yes in the polling under participants. Okay, well, I got 2 people that wrote me something. Yep, key is gravity. That's going to get a lot of you guys who are not careful. Okay, angular acceleration of an object is starting at 10 degrees per second and increases to 100 degrees per second in 5 seconds. Okay, so what is the angular acceleration? That's all we need to figure out is the angular acceleration. This is where I'm a jerk, because I give you more information than you need. So if this object's, okay, starting off, rotating, okay, at 10 degrees per second, and then eventually it's going to be going at 100 degrees per second. Find acceleration. All we need is what is effectively the change in velocity over the period of time it did so. So that's obviously looking for a uniform acceleration. That's very possible. So if we're looking for the angular acceleration of an object, starts at 10, gets to 100, well, that difference, what we're looking at literally is just going to be 100 minus 10, because we have final minus initial divided by 5 seconds, divided by the time it took for it to get there. So it's going to be 90 divided by 5, so it's going to be 18 degrees per second. It has a radius of 5 meters and a mass of 100 kilograms. That is just there to confuse you. Because like anything else, guys, just because you have all this information doesn't mean it's useful. You need to be able to focus on the information that really matters. Okay, so how much force needs produced if a lever has a resistance arm of 0.75 meters and 20 kilograms of resistance? When in doubt, draw it out. So it has a resistance of, so this is 0.75. This here is 20 kg. And a force arm of pulling us up. And this here is going to be 0.03 meters. Then we're going to have 20 times that 9.81 times 0.75 equals 0.03 times our effort. So then we're going to divide both sides by 0.03 and we'll have our solution. Yeah, guys, the key is draw it out. I mean, if you can visualize in your mind, that's great. If you can't, draw it out. Whenever we normally would have the exams in person, even though everything's on Blackboard, I would tell the students to bring in scratch sheets of paper and literally to, write everything out. So that way they could see these things, kind of visualize what's going on. Okay. Apex of flight, 10 kg medicine ball is 3 meters off the ground. Okay, notice I even tell you it has 3 meters to fall back to the ground. So, the med ball, it's 3 meters off the ground. It's traveling at the apex of its flight, which means it has no vertical velocity. So it's not going up any higher or going down any higher. It's just exactly going horizontally, and it has a horizontal velocity of 10 meters per second. Okay. What is the total amount of energy the object has? Well, that object has potential energy because it's 3 meters to fall back to the ground. So it's going to have, and the ball weighs what, 10 kg. So potential energy equals mass times gravity times height. So we literally have 10 times 9.81 times 3. But it also has kinetic energy, which equals 1/2 of the mass times the velocity squared. So then we have 10 again times 10 squared times 1/2. And so its total energy is going to be equal to that potential energy we just solved for plus the kinetic energy. All right. So hopefully we're good on that one. Now we're going to go ahead and move on to Haley's question. Sound good, guys? Okay, good. So what is the torque required to accelerate a rotating object if it starts at 10 degrees per second and increases to 100 degrees per second over 5 seconds and has a radius of 5 meters and a mass of 100 kilograms? All right, guys, now what does that sound like? That sounds like the exact same question I asked you before, only I'm not asking for the rotational acceleration, but it is going to be something we need to use. And this is where we have a lot of fun with math. So, okay, so when in doubt, draw it out. So again, we start here. Now we actually care about the other things. Altogether, the mass of this object is going to be 100 kilograms. The radius here is going to be 5 meters. We're starting at 10, and then we're getting up to 100 degrees per second. Now, the formula that we're going to use here is a little bit different, where our torque, okay, equals our inertia multiplied by our acceleration, or torque equals mass times radius squared times the acceleration. Well, the fun thing is you guys already asked me what the acceleration is here. Remember, that ended up being 18 because we go up to the speed in 5 seconds. So we start with 100 minus 10 gives us 90. 90 divided by 5 gives us 18 meters per second squared. That would be our acceleration. So we have, I'll put this over here, 18 times, well, we know the mass, which is 100, multiplied by a radius, which is going to be 5 squared. And so that equals our torque required in order to get it up to that rotational velocity. Questions? So guys, and I know you guys got to hear it from me yesterday for those of you in exercise physiology. It's all about principles. As long as we understand the principles behind what we're doing, we're going to be able to figure out the method that's going to allow us to solve this problem. So your principle is really asking yourself, what are we trying to solve for? What is the actual number that I'm asking you for? And so if I understand what I'm being asked, then I know what to use in order to get that. What angle is an object fired at if it hits the ground after 2 seconds, a total of 50 meters away? Okay, this is projectile motion. So, we fire the cannon. It's in the air for 2 seconds, and it goes a grand total of 50 meters. That's all we got to start with. That's all we need. So, how fast would this object have been going horizontally if it covered 50 meters in 2 seconds? Try a different marker because I realize this is coming in really faint. Perfect. So our horizontal, oh, there we go. Velocity is going to equal 25 meters per second. Because exactly that, we did 50 meters in 2 seconds. Done. Now, how the heck do we figure out that vertical velocity? Well, it was in the air for 2 seconds. So it was in the air for 2 seconds. We're going to use our vertical equation, which is we have 0 because we're going to hit the ground. Our initial velocity is a question mark times 2. And then we're going to do minus 1/2 of gravity times time squared. So from there, we're now going to go ahead and rearrange things a little bit. So the first thing we're going to get is 1/2 of 9.81 times time squared, which is going to be 4, okay, equals question mark, which is our initial velocity, times 2, because we've literally just added that to both sides. Good old factoring from algebra. Now, we're going to go ahead and divide both sides by 2. So we're going to have that as a cancel. If we've got, what's 1/2 of 4, guys? Good. And what's 1/2 of 2? Our vertical velocity literally equals 9.81 meters per second. So now we have both our vertical and our horizontal velocities, which means we could solve for our actual initial velocity, but we don't need that. We just need the angle it was fired at. So which of our trig symbols or trig functions are we going to use to figure out this solution?
Would it be tan since we have the horizontal and vertical component?
Exactly. Tangent, opposite over adjacent. Okay? So since we're going to try to solve for this angle, okay? So that'd be a good old theta. So we're left with is the tangent of the angle equals opposite over adjacent, which is going to be equivalent of 9.81 over 25. So then on your calculator, you would do that. You would do 9.81 divided by 25 and then inverse tan. So that's tan to the -1, and that'll give you the angle. So yes, Braden, you have to use the inverse. So that function, what it will effectively be, what we're really doing, guys, is we're multiplying each side by tan of -1. So then we're left with angle equals tangent of -1 of 9.81 over 25. Questions? You guys ready to work in groups a little bit? Awesome. Okay. Yourself, use the green marker in the future because that one actually you can read because it's actually bright enough that it matters. Now,